Hey. Hi all, thanks for joining. And in this open planetary lunch talk, we are very much happy to invite Michael Stephen Phillips. So Phillips is a research scientist at Lunar and Planetary Laboratory in University of Arizona. Phillips' research focuses on using remote sensing data and mathematical models to understand planetary bodies, their composition, geology, and geochemistry, formation histories, and potential to host life. Phillips has extensive experience with CRISM data processing and analysis, as well as the other hyper and multispectral reflectance and thermal emission datasets, topographic data, and various other satellite and small unmanned aerial system-based products. Phillips will talk about two new tools today. They are HyPyRameter and the Spectral Cube Analysis Tool CSAT, SSAT, or SCAT, that he has developed for specific use cases that arose in his own research and that he hopes others may find it useful. He developed HyPyRameter to calculate CRISM-like spectral parameters for mission simulation fieldwork. The Spectral Cube Analysis tool was an attempt to create a GUI environment to interact with hyperspectral image data. And we welcome Michael to speak about this very interesting topic.
Cool. Thanks for the introduction. And yeah, I'm excited to share these tools with y'all. I hope some people will find them useful and not too frustrating to use. Hopefully that will get better with time. So these two tools, HyPyRameter and SCAT, so the Spectral Cube Analysis tool, are both they were developed for working with reflectance, image data, and point spectra. And so I'll get into those a little bit more in the coming slides. But first, I wanted to give just a little background. So probably most people in this audience are familiar with NASA's Transform to Open Science, or TOPS initiative. And so this has been going on for a year or two now, and basically trying to set some standards for how we share our data and our software in the planetary community. And I think this is a really good initiative, and I'm excited for how this is going to go. And these two tools are trying to be in keeping with the TOPS initiative. So they're written in Python. I've been developing them on GitHub. Anybody can access the code. So hopefully these tools will be useful for people. And we just submitted a manuscript on HyPyRameter to Computers and Geosciences, and so hopefully that will be out in the coming months, and folks can look more into that. So I wanted to also say something about the current tools that exist for analyzing hyperspectral data in Python. There are packages that exist, and they're really great and very useful. So I just put a few of them here. So if your favorite tool isn't listed, I hope you're not offended, and reach out to me if there's something you find super useful that I haven't worked into my own workflows. PyHat, which is great for calculating spectral parameters. Spectral Python, which has a lot of different functionality for working with hyperspectral data. And then Rasterio, which is really great for just general purpose raster input and output, and has good all under the hood, so you can do all sorts of transformations and that sort of thing. And then I have on the other side Wiser, which is the workbench for working with hyperspectral images and data. And this is also a great tool. It's a graphical user interface and has some great functionality. So with these tools already out there in the ecosystem, why do we need more? So they're limited in one sense, which is that you kind of already have to know how to code to use some of these tools. And so we all know people who either don't know what Conda is, don't want to use Conda, don't want to become familiar with Git or any of these things where you're kind of interacting with the command line, or have to go in to the guts of a code to kind of get it to work for your purpose. And this kind of brings me to this point that there's no Python-based competitor to Envy out there, not really. Shout out to Wiser, but I would say it's not competitive with Envy, at least not yet. And the Spectral Cube Analysis tool is not either. but we'll talk more about what it can do and hopefully where I wanna take it. So that's kind of the reason. And then another small note is when we're working with these open source Python packages, there can be lapses in terms of how they're maintained. So for example, I, I was doing field work and needed to calculate spectral parameters for a specific purpose. And I just was having a real hard time getting PyHat to work. And it turns out that it was during a brief lapse and when it was being maintained. And so I just went ahead and developed my own package for that, which became HyPyRameter. Um, so yeah, there are some fits and starts that occur when you're working in this sort of open software environment. And so a high-level overview of these two tools. So HyPyRameter is for calculating parameters, and it's easy to install, but you still need to know Conda. So hopefully at some point I can come up with some easier way to do that, but that'll probably be wrapped up into the spectral cube analysis tool. And it still requires some knowledge of how to use Python. Uh, you kind of need to know how to at least run a Jupyter notebook, but I think at this point that's pretty low-hanging fruit. And it works on image cubes and point spectra, so it's somewhat flexible, and you can adjust the different parameters and make your own parameters and that sort of thing. But you have to dig into the code to do that. So building uh, graphical user interface sort of tools on top of that to build out your own libraries could be useful in the future. And then the SCAT tool allows you to interact with your spectral cubes. So this is a graphical user interface. You get to pull up the image and see it, surf around, poke at spectra and that sort of thing. And this is installed with a git clone command from the GitHub repo. And then you create a conda environment from an environment file, and then you start it up from the command line using Python. So here's just a screenshot from the README on the GitHub repo. So it's git clone, and then the conda environment create command, and then you start it up. And once you do, this is what you'll see. So this is the opening window. You can see places where the red, green, and blue bands for the display images. You can select different bands to display from the drop-down menus, adjust stretch values, and then there's some different functions over here. And so once you load in an image, you go File, load a hyperspectral cube, and then once you go through the File Explorer and select the cube that you want to load, this is what it'll look like. So this is an example of a emit image. So emit is a hyperspectral imager that was flown to monitor dust, but has, of course, other applications. And so this is from the Yungay Basin in Chile. And so this is for some work that I've been doing with a microbial ecologist monitoring a rain event. And I'll walk you through kind of the basic functionality of the spectral cube analysis tool in this slide. So one uh, sort of drawback for general purpose use of this tool is that it's meant to be used in tandem with a parameter image. So you'll notice that the right side of this screen is blank right now. And if you try to do anything in SCAT with just the hyperspectral cube, things are going to break. So you need to load in a band parameter image. And if you don't have one, you can calculate one using this tool. So the first thing you'll probably want to do is look at some spectra and select bad bands, so that way you're not incorporating those into your parameter calculations. So you go to processing, select bad bands, and that'll bring up this bad band selector interface. And so you have all the bands and the wavelengths over here, and then whether or not they're indicated as a bad band, so bad equals 0. And so you can span select the bad bands. So you can notice that these bands are no good. So we can go through and select those. So here's a little video of how you do that. So you just span select over that region, and then voila, those are now ignored. And if you scroll down on this table, you could refine which ones are selected by double clicking on this column over here. So, if the span select wasn't quite precise enough for your liking, you could go and refine that. So once you have the cube with the bad bands ignored, you can go and calculate your spectral parameters. And so that is under the processing window, and you pull up calculate spectral parameters. And so this is powered by the HyPyRameter package. And so this will run HyPyRameter under the hood, and that comes with the SCAT install. And so there are a few options. You can select a cropped region from your scene. You can turn on or off the bad band list, so that's the BBL option. You can interpolate NAND values, so if you have those bad bands indicated, you can just do a linear interpolation over that, and that will make the spectral parameter calculation go more smoothly. And then you can also run a denoise option, and this is powered by um, an iterative outlier voting filter. So this is basically just a statistics-based denoise option. And depending on the size of your image, that can take a really long time to run. So just beware of that. If you choose that option, you might be sitting for a few hours waiting for your cube to denoise. So once you have the option selected that you want, you click this initiate button. So that will set up all the parameters. So we click initiate, we select the cube that we want to run this on. And then we select the output folder. So I'm just putting this into a params tutorial output folder for the sake of this talk. And then this is what you'll see output on your terminal window. So we have the cube that we selected, we have the output directory we selected, we're setting the bad bands to NaN, and then this is a list of all the parameters. And so it says it took 2.25 minutes to load, but that was just because I was recording this, and so it didn't actually take that long. It only takes about 30 seconds or so typically. And so once that goes, you'll have this option to edit the parameters that you want to actually run. And so this is a list of all the parameters. And so you can see the list of all the parameters that HyPyRameter will calculate on this image. And this is based on the wavelength range of your image cube. And so you can select different parameters, and you could, if you wanted, you could add new parameters, but if they're not on this list, this is a list of all the valid parameters. So if they're not on this list, they won't run correctly. So I don't suggest adding parameters that are outside of this list. But say you removed a parameter and you're like, actually, I do want to calculate that one, you can add it back in. But if there's some parameter that's giving you issues or you don't need to calculate, you can remove them from the list. And so then you click close, and then we go back here, and then you can see I have this interpolate NANDs option selected because I do actually want to do that. And then we click run. And so this is what you'll see on your terminal window. So it's calculating all the bands. And then this will run for a few minutes. Let me skip forward a little bit. The longest one that takes to run is this rpeak1 parameter. It requires integrating over polynomials and can just take a while. But monitoring this terminal window, you can see whether or not this is running correctly. And you'll likely see some warnings about NAND slices in your rasters, which just has to do with either certain pixels that are have NAND values or bad pixels and that sort of thing. These warnings you can mostly just ignore and look at the outputs and see if they're reasonable. So here's the outputs from that process. And so now we have a parameter cube that we can load into SCAT. And it also spits out some PNG files, which are stock browse products that get calculated using HyPyRameter. So these are basically just for viewing. Maybe you can bring them into figures, but it's just to give you a sense of whether or not this ran correctly, so you can just view those. So let's go back to the spectral cube analysis tool and load back in our parameter cube. So we go to File, Load Band Parameter Image, and so this is the default parameters that it reads in, and then the default stretch options. And so you can adjust those down here. So you can manually enter the stretch values that you want. You can select the different bands that are being displayed in both the hyperspectral cube and the parameter image, and look for what you're wanting to look for in your image cube. So if you want to adjust the stretch options and you're not sure what the statistics look like, you can plot the histograms for the left or the right frame in the SCAT program. So here we want to plot the histogram for the parameters. And so this is what the histograms look like. And we can manually adjust the stretch. So using a span selection tool, we can select over this histogram to adjust the stretch values. So here's an example of me doing that. So I loaded in some different parameters looking for some different clays and across this basin. So we have aluminum and iron magnesium based clays that are going to show up with these different band depth parameters. So 2190, 2250, and 2355. So that's band depth at 2190 nanometers, 2250 nanometers, and 2355 nanometers. And so you can see compositional variability across this scene that seem to track pretty well with floodplains and channels. And so this is, of interest to the science I was doing across this scene. So let's say we want to draw some regions of interest and extract spectra from those. So we can open this draw polygons option. And so that will bring up this polygon menu. And we have a lot of options here. And some of these are going to be more or less specific to analyzing CRISM data, which was the original reason I developed this code. And so, for example, the column lock, if you want to draw an ROI and keep it in column, you can turn the column lock on. And then this draw polygons on and off button allows you to navigate around the scene without accidentally drawing ROIs. So you turn this on when you want to draw. And then you can remove the polygons from the display if you want to look at the image without them being covered up, and then you can redraw them back on. You can delete all the polygons. You can plot the mean spectra from your polygons, and then you can save them and then load back in files as well. And then this is, of course, the color of your region of interest. So let's turn draw polygons on, and I'll show you an example of drawing one. So I have a couple ROIs that I drew here. This red one, which is selected in the table, so it's highlighted in cyan there. And then this blue one here, looking at these different compositions. So here's an example of me drawing an ROI. So I'm going to zoom in on this green area here. And so like zooming and navigating around the image is done just with your scroll pad or using these navigation tools down here. Oops. Okay, so I drew the ROI, and then it takes a minute to load because it's calculating the statistics over the ROI after you draw it. And so there it is. There's the green region of interest. And now we can go back to the table, and we can see I have this red, blue, and green polygons. They each have their unique identifier over here on the left. And you'll see some options in this table. So you have a place to make comments, and maybe at some point in the future, I'll change these to more generic names. But for my purposes, I have mineral IDs 1 through 4, so you can make comments on what minerals you're identifying in that ROI. This template checkbox is for templating an ROI. So say you're doing CRISM analysis and you want to make a denominator region of interest for spectral ratioing. You can use an ROI that you've drawn as a template, and you check that. And then you go back to the windows and you right click, and that will copy and paste that ROI into the place that you right clicked. And if you want it to be in column, you turn the column lock on. And so you right click and it'll copy and paste that ROI in column for you. And then if you want to ratio your spectra, you have to click which ROI is going to be used as the denominator for that ratio. And so that's what this denominator checkbox is for. And then you'll also notice over here on the right, We have some metadata that will be saved with these ROIs. So say you've gone through your scene and you've analyzed the regions that you want to analyze, and you want to save this for future. Maybe you want to bring it in to Python and look at the spectra of these ROIs and do some other sort of processing and manipulation of them. The mean spectrum and the mean of all the parameters from your parameter cube are saved along with those ROIs. And as well, the wavelength vectors and the parameter vectors. So this is useful for processing your data later on. So let's see here. So here's an example of those red, green, and blue ROIs. So if we click that plot mean spectrum button on our polygon table, it will bring up this ROI spectral plot. And so for this plot, I've zoomed in on this 2000 to 2400 nanometer region, and you can plot library spectra. So I chose from a drop-down menu montmorillonite, and it has pretty good agreement with this absorption band here. And so you would go through and do your typical, spectral analysis workflow here, identify the minerals that you see in your ROIs, and then you could make note of them back on your table and be on your way. So here, for example, I've ID'd the red and green, maybe have montmorillonite, and the green ROI, I think maybe has some gypsum, so I've made notes of them there. And then, you could save this and share it with folks and yeah, do other analyses. So the other benefit here is when you save these ROIs, they get saved out as geopackage files. And the reason for this was because shape files were limited in terms of the amount of metadata I could store. So I couldn't store the whole spectrum as metadata in a shape file, but I could in a geopackage file. And so these files are, I think, a little bit more versatile, and you can still load them into your preferred GIS software in the same way you would a shape file. And so here are these same ROIs that I drew in the spectral cube analysis tool, but I brought them into my QGIS project. And so now I can see them overlaying on some other data products I have here. You could click on them and see the different attributes and the mean spectrum and that sort of thing. And so that's an overview of the main functionality that the spectral cube analysis tool provides. Maybe this will be of interest for your own personal workflow. You can integrate your spectral analyses of image cubes into your GIS projects, and it makes it easier for me, and hopefully other folks will find it useful as well. And so now I just wanted to go through a couple of other options that the spectral cube analysis tool provides. So you can extract spectra from the scene just by clicking on the scene. So in addition to drawing ROIs and extracting spectra from the cubes that way, you can extract point spectra. And if you wanted to collect individual points and not just regions of interest, you can do that by clicking the collect point option. So here's just a quick screen grab of me clicking on different points in the scene. You can see the spectral plot updating with those new points. Say you want to zoom in, and then you click this navigate option. You can pan around the scene. And so click on the screen region, maybe that's of interest, and then you say you want to collect that point and save it for later. So you collect the point, and that brings up this table, and it'll look familiar to you from the other table of the ROIs. And so these are your collected points. You can edit the name, you can edit the color, and then here's the X, Y in the image coordinates, and then the latitude and longitude. And then it saves also the spectrum again. If you had a denominator that you were using for ratioing, it'll save also the denominator spectrum, and then also the vector of parameter values. And then you can save this table out to an Excel file to do other analyses on these data. And so I mentioned that this tool was developed originally for my own work with CRISM data. So here's an example of CRISM mapping data pulled into the spectral cube analysis tool. I've drawn some ROIs over here. So this is my region of interest for some different minerals I'm looking into. And then this green region here is my denominator spectrum. Because typically with CRISM data, you want to ratio these spectra to get rid of residual atmosphere and dust that are obscuring some of the features that might be of interest. So pulling back up this polygons menu, you can see I have this green region selected as my denominator. I have my mineral IDs that I've made. If there's a couple of different minerals in that ROI, I put that as the secondary mineral. And then we can click this plot mean spectra, and it pulls up this ROI spectral plot. And then in this window, we can drop in some different library spectra. And so here I have a pyroxene. So this is an augite, so a high calcium pyroxene. And then this is an iron-rich olivine spectrum here. So it has some good agreement with these red spectra. Maybe there's a pyroxene absorption band here. So this is how you can sort of compare your spectra to library spectra using SCAT. And in the future, I want to add the minerals identified with CRISM analysis library spectra. Right now, the library spectra that are available are from the USGS spectral library. But I will be wrapping in mica library minerals into this as well, and hopefully some relab library minerals. So I've been reaching out to the relab team to see if there's an API, because the library spectra come with your SCAT install, so you don't have to go fetch these. But in an ideal world, I would be accessing library databases via an API, so that way you don't have to download those as metadata, making the install larger than it needs to be. But as far as I know, Relab doesn't have that option yet, but I hope it will soon. And so back to typical CRISM workflows. In addition to ratioing ROIs, you can also ratio point spectra. So say you're not sure you want to draw an ROI in a region, you're just kind of poking around to see what might actually be there. So here's a spectrum from a pixel. Here are the pixel coordinates. This is looking like olivine to me, and then I want to ratio it to a bland denominator. So I click on the scene with a left click, and then to place the denominator, I right click, and that will bring up this ROI spectral plot, or I'm sorry, this ratio spectral plot, where it shows me the numerator spectrum and the denominator spectrum. And then down here in the subplot, it'll show me the ratioed spectrum. And then I want to corroborate that this is actually an olivine, so I plot the olivine library spectrum on here, and it's looking like a pretty good match. And I can also plot it over here on the numerator spectrum. And so this is kind of a typical workflow you might want to be able to do. Okay, so that was a lot on the spectral cube analysis tool. As I mentioned, the spectral cube analysis tool has HyPyRameter sort of integrated into it. And so this is, I think, the easiest way to use HyPyRameter if you're somebody who doesn't want to code or doesn't want to use a Jupyter notebook, doesn't want to get into that. It's annoying to you to use that. I totally get that. You should use SCAT to run HyPyRameter, because it's just that sort of GUI interface. You check some boxes and you run it. If you want to use HyPyRameter on its own, you will need to work with some Jupyter notebooks and do some coding. So in order to install HyPyRameter, there's two different ways you can do it. So you can do this via Conda and just install HyPyRameter that way. So with this Conda install HyPyRameter command. And the other way you can do it is just clone the GitHub repo and then work directly from the cloned repo on your local machine. And so if you install this via Conda, I ran this Conda environment list command, you'll see an environment that looks like this. So this is my HyPyRameter environment. And you can see I have a couple of different test environments that I've been working on as well. So that's how you'll check and make sure your environment installed correctly. And once that happens, you go and you can open the example notebooks. So this is just some screenshots from the examples using point spectra. And so I'm highlighting the point spectra side of HyPyRameter here because we kind of already showed what you can do with the with image cubes in the SCAT tutorial. So here's the import lines. So you import the parameter calculator from HyPyRameter, and you want to specifically import the calculator that you're going to want to use. So in this case, we're importing the point param calculator, and then some other packages here as well. And then we instantiate the calculator. So we instantiate an instance of this class. So we have the path where our data are stored. So in this case, we have a CSV file with all of the spectra that we want to analyze. And so the HyPyRameter point param calculator class can read in pandas data frames, CSV files, Excel files, and these specific file types called .sed files, so .sed. So the reason for that is because these are the types of files that come off a point spectrometer that I was using in the field. And so if there are other file types that people want to see added to this list, reach out to me and I can add those. But those are the types of files that it reads in right now. So once you instantiate the calculator, it does this, it reads in the data and does this initial calculation to see what the valid parameters are, and then it will print those for you. And so this is the list of the parameters that will be calculated on these spectra. And then you can edit that list as well. So if you only want to calculate a subset of those, you can edit that list and store it into the valid param object or valid param list, which is a subset of the point parameter calculator object. So once you have the list set that you want to run, you simply just do ppc.run, and then that will print out the pandas data frame that comes out. And so these are the names of the spectra from the CSV file. And then this on the left-hand side here are all the parameters that get calculated. And so it's pretty much as simple as that. This calculation took about 30 seconds to run. And then you can take a look at your parameters and the spectra that you have. So I have some examples in the example notebook of just how to visualize some of these data. So here we just are simply plotting one of these spectra, and then you can plot the parameters as bar charts. So one, I guess, drawback of using parameters on individual spectra is that you don't get the same visual effect as calculating parameters across an image cube, where you can put in these RGB combinations of parameters and visually see compositional variation across the scene as colors across the scene. But you can look at these bar charts, and this can be a more easily digestible version of the information contained in a spectrum that you can share with people who aren't spectroscopists, which was the motivation for creating this. And so these are some of the options that you have with HyPyRameter. And yeah, so that's the end of the HyPyRameter tutorial.